All right. So I'm recording. Okay, good. So we're going to start talking about polynomials. This is for section 5.2. 5.2 introduces two types of functions: power functions and polynomial functions. And the power functions are really sort of just a simple case of a polynomial. So we're going to start with a little bit of vocabulary. The idea of a polynomial function is, and by the way, I'm going to put this document up on D2L, so you can print a copy of this and go through it with me. There's going to be some sort of interactive activity things that we do throughout here. Just wanted to mention that before we get started, so you can go print this if you want. So the idea of a polynomial function is just that basically it's a bunch of powers of x multiplied by constants and then added together. And this is how you write the generic format for that. So this is written out here with n as the highest power of x, and then the next power down is n minus 1, and then it'd be n minus 2, and so on until you get down 2, 1, and then this last term is x to the power 0, which equals 1. So you don't see the x to the power 0 right there, but you can imagine that there is 1 if you want. So now a0, a1 over to an, those would be constant real numbers. Okay, the subscript, which is that like n minus 1, 2, 1, 0. Those subscripts don't have any mathematical meaning. That doesn't mean some operation. Those are just labels. So the vocabulary here is that for a polynomial, the highest power, n, is called the degree. All those numbers are called, the multiples there are called the coefficients of the polynomial. And then the term with the highest power in it, which is an x to the n, that is called the leading term. It doesn't have to be the first one, so you can write these terms out of order, but it's the one with the highest power in it. The constant multiple, the coefficient for that term, is the leading coefficient. And then there's a coefficient which is called a0, which is multiplied by x to the power 0, which means it's multiplied by 1. So that really doesn't have an x factor at all. And that term is called the constant coefficient, or the constant term. It also happens to be the y-intercept of the graph of the polynomial function, by the way. So here's a few other facts about polynomial functions. The domain of a polynomial function is always all real numbers, unless you say otherwise for some reason, like real world context, for example, like the rock, stone in the air, moving in the air, like in the example from the last section. And then another fact about polynomials is that the graph is always smooth and continuous. That means no corners, breaks, or gaps, or anything like that. So let's take a look at some graphs of polynomial functions here. I'm going to come over here to Desmos. So y equals x to the power 1, or 2, or 3, or 4. Those are examples of polynomial functions. But you can also have stuff like y equals 5x cubed minus 2x squared plus x, or plus, 5 or something. You can have, let's see, 2 plus 1, so it's on the screen. You can have y equals x to the power 17, and then minus 2x, or something like that. Now, the idea is that these graphs are always going to be smooth and continuous, and they tend to sort of wobble back and forth. This one with the power 17, the green one here, it looks like it might have some sharp corners, but really it doesn't. Even something that looks sharp is not actually sharp. Okay, for polynomials, they're always smooth, and that's no matter how big you make this number. This is like 117, 1117. It looks really sharp, but if you zoom in far enough on that corner, you'll find it is not sharp. It is smooth, and it's a smooth curve. Okay, bends around. So that's kind of the overall idea with polynomials. You get different kinds of bendy graphs. They can wobble up and down a lot of different kinds. Like if you take x to the 4th and then you subtract squared, say like 3x squared, you can make it wobble up and down a few times. If you make this x to the 6th, subtract x to the 4th, and then add some x squared back in again. Oops. You can make it wobble up and down a bunch of times. Okay, so in general, the graphs of polynomial functions can have all kinds of wibbles and wobbles. It doesn't necessarily have to have any type of symmetry. Okay, but they're going to be smooth and they're going to be continuous. Let's learn a few other things. So as we are looking at these graphs, we're going to look at end behavior, which refers to basically where is the graph going on the left side and the right side. So as x goes out towards positive and negative infinity, what's the graph doing? Is it going up? Is it going down? Is it going towards 0? That's called end behavior. We're also looking at the turning points. Turning points are like local minimums and maximums. Same thing. So like this graph at here, it goes up and down a few times. It wibbles and wobbles. And those points where it reaches a local minimum or say a local maximum or another minimum, those are called turning points. So we're going to look at those. And then we're going to look at zeros, which is just another way of saying x-intercepts. So that would be like the points where the graph crosses the x-axis. Okay. So the first thing we're going to do, and you can follow along with me here if you want, we're going to graph y equals x to the n. Those would be called power functions. We're going to graph the first few of those, and we're going to pay attention to the degree, which would be the n value, and the end behavior. Let's see if we can find a pattern. So here's x to the power 1. There we go. That's the line, and its end behavior is down on the left and up on the right. X to the power 2, up on both sides, approaching infinity on the left and the right. Okay, what about x to the power 3? 4, 5, 6, 7, 8, 9, 10. And I think you can see 12, 13, 14, 15. It's alternating back and forth. If you could see me, I would do I had my camera on. I would show you the polynomial dance. But alas, we can't do dances in class any longer. It's a bummer. There's a lot of good dances to do in this class. Maybe I'll show you in a meeting sometime. So what we see is the end behavior is kind of going back and forth. So we could describe this by saying if n is odd, you have down on one side and then up on the other side. If n is even, you have up on both sides. That's for so far just straight up regular old power functions. Now, if you do the same thing, but you throw a negative in front, okay, let's put a negative in front of that, then suddenly it reflects over the x-axis, and everything is opposite. Okay, now we're alternating between up on the left and down on the right versus down on both sides. So we could express it like this. If n is odd, we have up on the left, down on the right, versus if n is even, we have down on both sides. So the end behavior seems to depend on the degree, whether that n value is odd or even, and it also depends on the coefficient, whether it's positive or negative. Okay, those are the two pieces of information that the end behavior depends on, and this is true for polynomials as well. So you can graph these specific polynomials. We're going to graph a bunch of different things here, like let's pull these back. This is 5x cubed. So x cubed, 3 is the degree, and we see that the end behavior is opposite, down on the left, up on the right. If I made that a -5, it flips around, right? On the left, down on the right. Nothing else about this is going to change that. So if I change that next coefficient from a negative to a positive, that doesn't change the end behavior. If I change this from a minus to a plus, shifts the graph around, but it doesn't change the end behavior. I can put another x on here. I'm going to put another x squared on there. But not anything else I do doesn't change the end behavior. And the actual value of this leading coefficient, whether it's 5 or 3 or 9 or whatever, doesn't change the end behavior. It's just whether that's positive or negative and whether this is odd or even. So let's sum that up. So in this little chart. So we have two things that this depends on. One is the degree is odd. The other, whether that's odd or even. So that's one of the things it depends on. The other thing it depends on is an, the leading coefficient, being positive, or an being negative. So I wrote greater than 0 or less than 0 for positive versus negative. So it is the degree, or it's called the parity of the degree, even or odd, versus, and then the sign of the leading coefficient. So in the first case, you can write as x approaches negative infinity, that would be on the left. F of x approaches what? So this is the situation where we're talking about an odd degree and a positive leading coefficient. We saw in our or rather, let me go ahead and draw that in here. We saw in our exploration that it was down on the left, so we'd write negative infinity here, and up on the right, so we'd write positive infinity here. So that is the general characteristic of when it's odd degree and positive leading coefficient. If it's odd degree and negative leading coefficient, it was up on the left and potentially wiggles and then down on the right. So that'd be the opposite. As x goes towards negative infinity, which is left, f of x goes towards positive infinity. And as x goes towards positive infinity, f of x goes towards negative infinity. Now degree, even degree, is where they are the same on both sides. So if it's positive leading coefficient, it's up on both sides. And if it's negative leading coefficient, it's down on both sides. So this is our table for remembering how to figure out what the leading coefficient is. Sorry, how to figure out what the end behavior is based on just those two pieces of information about the polynomial. So now there's some other information like turning points and polynomial zeros. So what I want to do is, I think maybe I might stop this video and make a new one because this is getting kind of long. So we'll stop and pick up right here in the next